Today I'm going to talk about the complex numbers, which is a fascinating field of mathematics. At first, the name complex numbers may seem a little daunting because complex means complicated, but really they're not actually all that complicated. They're just compound numbers. They are numbers made up of two different parts. First, we need to talk about squaring numbers. Squaring numbers goes like this. Let's say we have a number x and we raise it to the power of 2. That means x times x. So for example, if we have 3 squared, that means 3 times 3, which is equal to 9. So 3 squared is 9. But what happens if we have negative 3 and we square that? Well, that's negative 3 times negative 3, which is also 9. It's not negative 9. If you square a negative, you get a positive. And if you square a positive, you also get a positive. You need these brackets because of order of operations. I think we touched on that in our video about reverse Polish notation. I'll put an annotation on the screen around about here. But if I didn't have these brackets, this 3 squared would be done before this negative. So it would look like that. That is going to be negative 3 times 3, which is going to be negative 9, and that's not what we want. We don't want to square the 3 and then make it negative. We want to square the negative 3. So now we have square roots, which are sort of the inverse of squaring. So if we have x squared, the square root, which is written like that, the square root of x squared is going to be x. So for example, up here we know that 3 squared is 9. So if we have the square root of 9, that's going to be 3. I've also said above that negative 3 squared also equals to 9, but this square root notation exclusively refers to the positive one. We could say plus or minus the square root of 9. That's going to be equal to either positive 3 or negative 3, which is written like that. So finding the square root of 9 asks a question. It basically says which number that when you multiply it by itself, it gives you 9. And I've said before that when you square a positive, you get a positive. And when you square a negative, you get a positive. So what happens when you try to get the square root of a negative? What number, when you square it, will give you a negative? There are no real numbers that, when you square them, will give you a negative. And a real number, by the way, is any number that fits on this number line. Here we've got 0 here, we've got 1 here, we've got negative 1 here, we've got even irrational numbers. We've probably got pi around here somewhere, and maybe e somewhere here, and root 2 will all be there somewhere. Any number that we can assign a value to, that includes fractions, irrationals, transcendentals, all numbers like that are real numbers. If we can put them on this number line, they are real numbers. So let's imagine that there is some sort of number that when you square it will give you negative 1. And we will call this number I. I is not a real number. It doesn't fit anywhere on this number line. It doesn't have a real value, which is why we call it an imaginary number. I is short for imaginary. That's not just any variable name. I, when you're talking about complex numbers, means the square root of negative 1. I is defined so that I squared equals negative 1. That's how we define I. We're essentially creating a new number. But if this number doesn't fit anywhere on the number line, how are we supposed to represent it graphically? And that's where the complex number plane comes in. As well as having our real number line here, we also have another axis. Here we have 1, 2, 3, and also negative 1, negative 2, negative 3. But up here we have I, 2i, 3i, and here negative I, negative 2i, a negative 3i. And now we can represent I on this. This is called the complex plane. Any point on this plane can be represented as the sum of a real number, that is a number that can fit on a one-dimensional number line, and a multiple of I. For example, let's say we have a number at this point. This number here is 3 plus 2i. It is 3 on the real axis and 2i on what's known as the imaginary axis. And this number here, 3 plus 2i, is a complex number. It is the sum of an imaginary number, that is to say a multiple of I, and a real number. So any number that fits on this plane is a complex number. And it can be written in the form a plus bi, a real number plus a multiple of I. And real numbers are in this form. For example, this number here, the number 1, can be written as 1 plus 0i, and therefore it is a complex number as well as being a real number. Also, imaginary numbers, for example, here, I, those can also be written as complex numbers, 0 plus I. So what can we do with complex numbers? Let's choose 2 different complex numbers. Let's choose 2 plus 3i, and let's also go with 3 plus 5i. Those are both examples of complex numbers. And what happens if I want to add them together? Well, that's simple. We just add the 2 real parts together, giving 5. And then we add the 2 imaginary parts together, giving 8i. And that is the sum of these 2 complex numbers. Now, what happens if we want to subtract them? Let's subtract 2 plus 3i from 3 plus 5i. That, again, we just subtract the real part, leaving 1. And then we subtract the complex part, leaving 2i. And much in the same way that if we had 2 numbers on a number line that we want to add together, we add their distances from 0. We do the same with the complex plane. Going back to this graph from earlier, if I take this complex number here and this complex number here, if I want to add them together, we take this distance here and this distance here, and we add them together, which will give a number up here. Much like adding vectors together in maths or physics.
Which we might cover later.
Ooh. You can also multiply complex numbers together, much in the same way you would multiply any binomial terms. So for example, if we want to multiply these together, we could do that in our head, or we could do that with the expansion, but I'm going to show you what we've learned at school as a farmer's field method of multiplication. So we separate them. We separate both of these into 2 terms. So we have the 2, and we have the 3i. And then we will also separate this into 2 terms. So we have the 3 and the 5i. And we're just going to draw a grid like this. And in this box, we multiply the 2 headings together. So this is 2 times 3, which is 6. This is 3 times 3i, which is 9i. This is 2 times 5i, which is 10i. And here we have 3i times 5i, which is 15i squared. And if we add these all together, we will get 15i squared plus 19i plus 6. But wait a minute, this doesn't look like a complex number. Complex numbers have to be in the form a plus bi, and we've got this pesky I squared term over here. But if we remember back to before, I squared equals negative 1. That's how we define I. So 15i squared is negative 15. So we can rewrite this as 19i plus 6 minus 15, or if we want, 19i minus 9. And suddenly, this is a complex number again. So we can expand on this. If we have I squared equals negative 1, what stops us from getting other powers of I? So we have I, then we have I squared, which is negative 1. Then we have I cubed, which is negative I. Then we have I to the 4, which is 1. And then you have I to the 5, which is I again, and it'll just follow in this pattern. It'll go to -1, -I, 1, then back to I again. So it follows a pattern like that. What are complex numbers actually used for? And there are so many applications of complex numbers, including real-world scenarios. For example, if you want to describe a circuit, in a circuit, generally speaking, the voltage is inversely proportional to the current. So if you could describe the entire circuit as one number, the voltage plus the reciprocal of the current times I. And that way you could double the circuit, or you could half the circuit, and everything will remain intact. A prominent use for complex numbers, and my favourite use for complex numbers, is rotating points in 2D. So let's draw out a complex plane. So remember before when we were talking about multiplying complex numbers? And I didn't show that on the graph, I wanted to save that for later, because there's a lot to talk about with representing the multiplication of complex numbers on a complex plane. When you have a complex number, for example, I'm going to have the number 2 plus 3i. As well as being 2 plus 3i, you can also represent that as a distance from 0, and also an angle from the real plane in an anti-clockwise direction. And I'm going to call this angle theta. Let's say I have another complex number. This is going to be -1 plus 2i. That is also another distance, and it is also another angle, and I'm going to call this one alpha. If I multiply these two numbers together, it will give me a resulting complex number which has a distance from 0, which is this distance here multiplied by this distance here, and it will have an angle that is this angle here, theta, plus this angle here, alpha. So the result of this multiplication here is -8 plus I, which, that was a badly drawn line. Its angle here is theta plus alpha, and its length here is the product of these two lengths here. So, let's say I have a point and I want to rotate it a certain number of degrees. Let's take this point here, 5. 5 plus 0i. And I want to rotate that 90 degrees anti-clockwise. Well, I want to find another complex number to multiply it by, whose angle is 90 degrees anti-clockwise from the real axis, or it's perpendicular to the real axis, and its distance from the origin is 1. And that number is here, I. It's perpendicular to the real axis, and it has a distance of 1 from the origin. So let's take my number 5 again. If I multiply that by I get 5i, which works. That's a 90-degree rotation, anti-clockwise. If you want to rotate any point, if I started, I don't know, here, 4 plus 4i, and I multiplied that through by I, that would have given me a 90-degree rotation, anti-clockwise, to here, 4i minus 4. If you want to rotate any complex number, or a point in 2D space, which has been turned into a complex number, you just multiply it by another complex number, whose distance from the origin is 1, and whose angle is whatever angle you want to rotate your point by, anti-clockwise. So that's a brief introduction to complex numbers. They're incredibly useful in mathematics, and hopefully they are not as complex as they may first appear.